Great. Okay, so that was observational studies and experiments. Just a quick check. Do we ever use placebos in an observational study? Never, right? Okay. Placebos are only used for blinding, and you'd only do blinding if you're assigning treatments in an experiment. Observational studies, the patients get to subjects get to self-choose. Okay, and then just a quick note about sampling. And we already talked about sampling in the very beginning of the class, and the idea again being we have a population that is too big to study directly, so we take a little piece out. This is called the sample. And this process of selecting people from the population in our sample is known as sampling. Okay? How do we select people? People or subjects, if we're talking about rats or something, from the population. So that process is known as sampling. Okay? Now, for our conclusions, for us to do inference about the population based on the sample must be representative of the population if we want our inference to be valid. Okay? So one method that should, doesn't guarantee, but should give us a representative sample is known as simple random sampling. Okay, but I will also write does not guarantee did I spell that right? Guarantee a representative sample. But just mathematically, it should give you a representative sample. And the idea behind simple random sampling, or SRS, start with a sampling frame. Okay, the sampling frame is everyone that can be selected to be a part of the sample. To be part of the sample. Okay? In an ideal world, in the ideal case, the sampling frame is a list of everyone in the population. Is a list of everyone in the population. Okay? That is the ideal case. That being, everyone in the population would be in your sampling frame, and therefore, everyone can be selected to be part of the sample. The difficult thing is getting a list of everyone in the population. If I said, we want to take a random sample of people living in Los Angeles County, does anyone have a list of every single person living in Los Angeles County? No, that thing doesn't exist. Okay? We take a census once every 10 years. That thing is already 5 years outdated, and we are closer to the next census than we are to the one that we took. And you know, it's hard to have a list of everyone, you know. And since 2010, lots of people have been born, lots of people have died. It's already outdated. So we try our best, but it's not going to be perfect, okay? And so if you have flaws in your sampling frame, you will have the same flaws in your random sample, okay? If your sampling frame doesn't include homeless people, then your random sample won't include homeless people, okay? And that's a problem. That's a known issue in trying to get random samples of people. If people don't have a permanent address, it's kind of hard to track them down. So that's just something to keep in mind. Maybe it doesn't matter in the study that you are doing, but that's something you have to keep in mind. Okay, so anyway, whatever you have. Let's say you have your sampling frame. Simple random sampling is just like it sounds. You just select individuals from the sampling frame one by one at random. Individuals from the sampling frame one by one at random. Okay. And we used to have to spend time in the course talking about how to select things one by one at random. Today, all I say is go to a website like random.org, and they have tools where you can put in a list of things and say, I want you to randomly select 20 people from this list, and it will do it, okay? We have computerized tools to help us with this task. Back in the day, I mean, even you know, you would have these random number tables, and you would use that. But that's like teaching people how to use a slide rule today. Okay, we don't. It's unnecessary now. Okay, we have computers to do all of this. Okay, there are other sampling methods that are non-random sampling methods that help us get representative samples, and I will leave it to you to do your reading to read about these methods, and they are cluster sampling and stratified sampling. I just want to make sure that they are in here.
In the reading cluster sampling, it said that they weren't going to talk about it until later in the book.
Okay, yeah, I mean, they're just terms, you know. So in this class, we are not going to spend a lot of effort in sampling methods, okay? You can take another course talking about sampling. Pew Research is an organization that has spent lots of energy and time trying to figure out how to get good samples, because when they survey people, they want it to be representative of the United States. And in this class, I'm just kind of going to wave my hands and just say, here's some data. We're going to pretend that it came from a random sample. That's probably a very dangerous assumption to make, to assume that the data you have is coming from a random sample. But on a practical level, in an introductory course, we can't spend a whole lot of time going over complicated sampling methods, okay? Because, you know, Pew Research, they have this, right? I wrote one line here. In the ideal case, the sampling frame is a list of everyone in the population, okay? Pew Research has spent lots of energy trying to figure out how can we get a good sampling frame which has everyone in the population, okay? And we're just not going to really invest the energy into that. So I'm just going to say, well, we're going to pretend like this is possible, and our data is going to come from pretend simple random samples. But in reality, this is a difficult thing to achieve, okay? Okay, but other methods, stratified sampling, and cluster sampling. Okay? Do your reading here, okay? And yeah, you can take an entire course devoted to sampling, okay? Especially if you were to work for a research organization like Pew Research, which is how we get, you know, all of these approval ratings and public opinion polls that we deem to be trustworthy, is because people have invested time in trying to get a good sample. But that, you know, so that should also tell you that if you go to a website, any news website that has a poll, it's not going to be a simple random sample, right? You could ask, you know, the Supreme Court made a decision today. You can go to, let's say, Huffington Post. If they had a poll, how do you feel about this? I don't think they do, but how do you feel about the decision? The results of the poll there will be different from if you go to Fox News and say, how do you feel about this decision? Okay? And it's because visitors to those websites are not representative of the United States. Maybe if you took, yeah, I don't think there's any one website in the entire internet that would be a representative sample. Maybe Google, I don't know.
Fox News would say that they're a representative sample.
You know, so, you know, every organization likes to think that they get a representative sample, but it is truly difficult to get a representative sample.
A lot of commercials on TV are fake samples.
So yeah, you know, 4 out of 5 dentists recommend this. I don't, you know, maybe. Okay. Okay. Anyway, let's get into descriptive statistics. So this is now chapter 2, and descriptive statistics. Okay. And so, you know, we have an hour left in class, and I've got this entire chapter to cover, and so I'm going to have to kind of pick and choose things to cover, spend time in lecture to go over, and leave other things as part of your homework to do in the reading, okay? And I feel comfortable doing that because I think a lot of the terms and concepts in this chapter are already familiar to you, like finding the mean, finding the median. Well, I assume all of you guys know how to find the mean of a set of numbers and things like that. But let me just say this about descriptive statistics, okay? We have a data set, okay? And a data set can be thought of as information about the sample that, you know, we're observing, okay? So again, we aren't observing the population, we observe a sample. Okay, and the data set is information about the sample we observe, and it's generally organized into rows and columns. Organized as a table. With rows and columns. Okay? Every subject in your sample in the data set will have its own row, okay? Every subject has its own row, okay? And each variable has a column, or each column is a variable. And so this would be our raw data table. Okay. And we have 2 types of variables. We have numeric variables which all measurements are numeric variables. And these tell us how much or how many? Okay, and then we have categorical variables. And these tell us what type or what kind. Okay, so just imagine we collected data on people, and we could say, you know, Joe is male, his weight is 152, and his height is 70 inches tall. Okay, and Jane is female, she weighs 115, and she is 5'4", 64 inches. Okay, and so in this case, sex would be categorical, weight would be numeric, and height would be numeric. Okay. Simple enough, right? Let's say I gathered another piece of information. What zip code they currently live in. Is that numeric or categorical? Zip code. Yes, it would be categorical. So let's say Joe lives in 90210, okay? And Jane lives in 90095 or something like that, okay? We cannot say Joe has 115 more zip code than Jane, okay? That doesn't make sense. You can't make that kind of numeric comparison. You can say that with height. You can say Joe is 6 inches taller than Jane. Joe is 37 pounds more than Jane. You can say that. But you can't say Joe is 100 whatever zip code more. Okay, so this would be categorical. Okay. Then we have descriptive statistics, okay? We have summary statistics. Okay? Summary statistics, these include things like the mean and the median, no problem. Okay? So the mean and the median are summary statistics. Also things like the standard deviation, and we'll get into all of these, okay? Standard deviation, the range, the IQR, these are all summary statistics, okay? And and by the way, these summary statistics, these all apply to numeric variables, okay? And you can have a summary statistic for categorical variables, and that would be things like the count or proportion. Also summary statistics, but these ones are for categorical ones. So we can talk about the proportion of the class that's female. Okay, and that would be a summary statistic. You wouldn't talk about the proportion of weight. You know, you would summarize that with the mean or median or standard deviation, range, or IQR. Here's the point of summary statistics. Okay, we don't calculate the mean just for the sake of calculating the mean. I mean, I guess we could, but the idea, the reason why we bother with these is that they provide a summary of the data that we have. You know, let's say our sample consisted of 200 people. Okay, now I could, and somebody wants to know about the 200 people we observed, I could give you the raw data table. There would be 200 rows and however many columns and things that we have. And maybe that's of interest to you. But a lot of times people don't want to have to look at all 200 people individually and try to make a decision or something based on that. Okay? And so a summary statistic basically takes all of that information and just crunches it down into one single number. And this one number is supposed to represent what's in that 200 data points. Okay? And that's useful, but you have to keep in mind that it's just a summary and you're going to be missing aspects of it, okay? And an over-reliance on a summary statistic can also be detrimental, okay? So for example, when you were in school, or you are in school, you had this thing called the GPA, all right? And that single number is supposed to encapsulate what kind of student you are, okay? All of the classes you took and all of that's supposed to get captured in one single number. And you know, if you're a 4.0 student, it says something about you, and if you're a 2.3 student, it says something else about you. But to then reduce a person into just a single number also fails to capture you know, the essence of the person, or whatever you want to say. Anyway, that's what we have, okay? Summary statistics, the mean and the median, standard. Okay, we could throw GPA in here as a summary statistic, but these ones here, the mean, median, standard deviation, range, IQR, these are kind of universal, can be applied in any setting, okay? Any setting with numeric data, whereas the GPA is a summary statistic that applies only in the setting of academics in the United States, okay? If you go to Germany, they have something else. They have a GPA, but it's not. 4.0 would be a bad GPA. So anyway, that's what I want to say about summary statistics. And we have, you know, summary statistics for everything else too, right? And, you go to Rotten Tomatoes, and then you've got a movie has a 98% fresh rating versus 60% fresh, okay? Does that mean you'll like the movie that's 98% fresh? No, because we don't even know what that movie's about. Maybe you hate animated movies and so you don't want to watch Inside Out, or maybe you like the actor, whatever, okay? Anyway, so that's that. The mean and the median are measures of center. Are both, I should say, summary statistics describing the center or central tendency. Okay. And I think you guys already know how to calculate the mean and the median. The mean can be thought of as the balance point of our data. And the median is the halfway point of our data. Okay, so the halfway point meaning once you find the median, half of the data is larger and half is smaller. Smaller than the median. The mean, as far as balance point goes, let me see if I can find it in this book here. Are. Okay, so imagine you take data points. So here is the data points 1, 2, 10, 10, 11, 13, and 19. Okay, so we're taking these data points and we're putting them on this number graph, right? 1, 2, 10, 11, 13, 19, okay? And imagine this being like a seesaw. If I put the little balance point, the fulcrum right here, this is where the seesaw would be balanced. Now if I moved the balancing point over here, this says if this were a seesaw, it would be tipping over this way, okay? And so the mean is the spot where the data points would be balanced, okay? Here's another thing, okay? So the mean is influenced by outliers, okay? Influenced by, I'll say, extreme data points. And the median is not influenced by extreme data points. Okay? And so depending on your situation, you may choose to describe the center by using the mean or the median. And you want to think what is a more appropriate, do I want this thing to be influenced by extreme data points, or do I not want it to be influenced by extreme data points, okay? And so I'm going to borrow an example from that book, What is a P-Value Anyway? But, you know, imagine a diner, and we have a diner in a coal mining town or something, and you've got 5 people working from the coal mine, and, you know, and we ask, you know, what is the average income of people in the diner, okay? And maybe the incomes are, you know, 60,000, 60,000, 60,000, 60,000, and 70,000, okay? So you got 4 people and maybe the foreman or whatever. And so you do 60 plus 60 plus 60 plus 60 plus 70 divided by 5, and you get the average, the mean, is equal to 62,000. And the median, okay, we have 5 numbers, right? So 5 divided by 2 is 2.5. So I should have 2.5 larger than the median, 2.5 smaller than the median. So basically I'm going to go right here, and I would have 2, if I pick this number, I have 2 numbers smaller than it and 2 numbers larger than it, or at least equal to and larger. And so my median would be exactly 60,000. Okay, so this is what we have here. Let's say Bill Gates walks in, okay? And so now we have 6 people in the diner. And I'm going to put Bill Gates in, let's say Bill Gates makes $10 million a year. He probably makes more than that. But let's say he makes $10 million a year, okay? So now what is the mean and median income? So with Bill Gates, okay, the mean is now much bigger, and the median is what? The median is still 60,000, right? It's now in between this, right? I would have 3 numbers bigger and 3 numbers smaller, so the median would be 60,000. I have 3 numbers at this point, and the mean, I would have to add up all of these numbers, 10 million, 60, 1, 2, 3, plus divided by 6 people. Okay, so the mean income is $1.718 million. Okay. And so someone says, what's the average income of people in the diner? What do you think you should tell them? What's the typical income in that diner? 60,000 or 1.7 million?
60,000.
Yeah, well, I don't know. It's hard to say. Okay, it depends. It depends on the situation, all right? Now, probably if you're going to say typical income, you would say 60,000, okay? But then if somebody says, well, let's say I want to provide insurance for everybody, you know, AFLAC, okay? We want to make sure we can replace lost income if these people were to die. Should we say we get everybody 60,000 income policy, or do we need to do something bigger than that? Probably bigger, right? Because if we lose Bill Gates, then that's a huge loss, and to just say the average was 60, we would be missing out. Okay, so depending on the situation, you may or may not want your summary of center should be influenced by extreme data points. Okay, and I guess that's to kind of just say, think of what the the reader or whoever wants. Think of what they might expect, and you should present the information that you think that they might expect. And maybe it means you got to present both the mean and the median, or whatnot. Okay, depending on what you have, it could be misleading to choose one number over the other. There was some example of a college said, come to our school because our graduates are successful. The average income of our alumni in 2010 was $85,000 or something like that. Okay, and that was because one of the kids got drafted to go play in the NBA, and so he made millions of dollars, and the mean income was brought up to 85,000. So were they lying? No, that was actually truth, but it could be misleading because maybe that's not really what people were expecting to see. So anyway, that's what I have to say about mean and the median. Okay, I want to talk about shapes of distributions here. Okay, so when we're talking about a numeric variable, we have shapes of distributions. Okay, so we have a graphic display called a histogram that we can use to show data that we have. Okay, so for example, here is what we call a frequency table. This is one way to summarize data, and this is a frequency table. So you can imagine it says 36 here. So in our raw data table, how many rows would we have had? 36. We would have had 36 rows because there would be one row for each, in this case, sow. All right, so we looked at a bunch of different sows and how many piglets they had. Okay, so these are pigs having pigs, and 36 different pigs gave birth to more, and I guess the number of pigs that survive is different. So one sow only had 5 piglets survive, and there were 2 sows where 14 piglets survived. And
this is 0 though, is that?
Yeah, so this means there were out of the 36 sows that gave birth to piglets, none of the sows had only 6 pigs surviving. Okay, so we had one sow where only 5 piglets survived. There were no sows where 6 piglets survived. There were 2 sows that had 7 piglets surviving. Okay, does this make sense?
Why would they put the 0 in there, though?
For completeness, I guess, because you go 5, 6, 7, 8, 9, 10, 11, 12, 13. I don't know. We're counting. So I guess it would be a stylistic choice. It is not wrong to take out the 6, but generally when you're presenting a summary table for numeric data, especially ones with integers, you would include from the smallest number 5 to the largest number 14, you would include everything in between. Okay, unless you're dealing with Bill Gates with 10 million, and then you don't want to have to write out everything out there. Okay, so this would be a frequency table. Okay, so maybe I'll just include this, and I just want to make sure we can read what this table says. Okay, so this means 36 sows in our sample. Okay, one sow had 5 piglets survive. There were 2 who had, or 2 that, I don't know, had 7 piglets survive. No sows had 6 piglets survive, okay? None of the 36 sows had 6 piglets survive.
Each of them had a survival rate.
Yeah, well, you know, it doesn't even say, like, because it's not like all of the sows had the same number of piglets born, okay? But, you know, so maybe this one gave birth to 5 and all 5 survived. We don't know. This doesn't say, okay? It's just saying this is what happened when the piglets were born, okay? And I'm not familiar enough with pigs and animal husbandry to know what a good number is, okay? But it seems like most or a good number had 10 or 11. This seems to be kind of a typical rate, okay? This seems to be, quote, typical. Who knows? Okay, so we can display, so this is one way to summarize, okay? So rather than having a table with 36 rows, we can summarize it with this thing. This is called a frequency table. So we have that, okay? And then we can make a graphic display. And up here, this is called a dot plot. Okay? So all we're doing for this graphic display is we're taking each number, okay, and we're drawing a dot. So this 5 right here, the one sow that had 5 pigs, she is represented here, okay? You see there's no dots at 6 because there were no sows that had 6 piglets survive. The 2 sows that had 7 piglets survive, they show up right here, okay? There were 9 sows that had 10 piglets survive, and they show up right here, and we can see how the data gets displayed here. Is this okay? So this is called a dot plot. Are there any questions about how we got here? Okay. And if you don't like dots, you can turn, whoops. You can turn them into bars, okay? And this is the exact same data, except instead of dots, we put bars. And so instead of having one dot, we have a bar that is of height 1. And instead of having 2 dots, we have a bar that's of height 2, okay? And this thing is, and this is called a histogram, okay? This is a histogram. And so so a histogram is a very commonly used tool. Okay, and let me see if I can shrink this down and stick this right here. Okay, so this is the exact same information, exact same info. And this is a histogram. Okay. And so when a lot of times you won't even get the frequency table, you might just see the histogram, okay? And so when you see the histogram, you should be able to infer back what the frequency table says, okay? So if you see a histogram like this, you see, oh, here we have a bar right here. This represents one sow that had 5 pigs. 5 piglets survive. Here I have a bar of height 2. So if I said, you know, how many piglets survived to the sow that had the most number of survivors? And you would say, oh, well, the one that had the most surviving is over here, and there were 14. Okay. Is that okay? Yes?
Do all histograms have the number that they're representing, where it starts?
Yeah, so this is just kind of the convention. You know, one could argue that the bars should be centered at 14 or something like that. The convention has become that this bar between 5 and 6 represents the interval. I don't know if you're familiar with square and curly brace notation, but the bar that goes right here represents 5 and including everything up to but not including 6. Okay, and so this bar would be the one for 5. Okay. And so
the frequency tables, the bar plots, and the histogram, all representing the same thing.
yeah, this is all the same data here. Okay, so yeah, this is the convention. Is this? That's who am I to challenge that convention? But that's how it is. It's not wrong if you decide to use a different thing, but you might want to define that or explain that because people might be accustomed to seeing this. Okay. Okay, so yes, so these things all show the same information. Okay. Let's look at a few more histograms. Okay. Relative frequency, basically you just turn a count into a percentage. And this, I'm sorry, that applies for categorical variables. So here is another example where here's 36 different values that we gathered, okay? And they are not sorted, but we could sort them. And then we decided to make bins. So with the sows, it was easy. We just said how many had 5, how many had 6, how many had 7, okay? But here, you know, we can see the range going to as small as 25 and as large as 203, I think, okay? And so it would be, we would have an incredibly too many numbers to go list off everything from 25, 26, 27, all the way up to 203. So we created bins, okay? And so we have a bin starting at 20, going up to but not including 40. How many people have cholesterol levels between 20 and essentially 39.9? One person, this guy right here. How many people have cholesterol levels between 40 and 59.99, okay? And then we can count and we would see there's 4 people. And we go and we fill out the frequency table this way, okay? And then we can turn this into a histogram. So is creation of this thing okay with everybody? Okay? So we turn this into a histogram and we get this, okay? And so I want to start talking about the shape of this distribution, okay? So we're going to be describing the shape of this, so because once we turn it into a histogram, we have this visual representation, and we can talk about the shape of this But keep in mind that when we're talking about the shape of this distribution or this histogram, we are talking about the shape of these underlying numbers and essentially the underlying cholesterol values. Okay, so whenever we talk about the shape of a histogram, keep in mind that there are actual values underneath that. Okay. So when we talk about shape, there's a few things we want to point out. We want to talk, say, so let me create a little thing here. We want to talk about the number of peaks that we have, okay? And so it seems, I would say there's really only just one peak. And we have to decide, well, is this symmetric or not? So it seems most people, so we're talking about this, and it seems like most people are kind of in this range here. Okay, and we know that most people here, because the bars between 60 and 120, these bars are the tallest. Okay. Okay, so the bars for 60 to 120 are the tallest. So these bars represent the most number of people. Okay, and then we have a few out here. You know, some slash a few, and then also some and a few down here. Okay, and we kind of have to talk about, so this would be the peak, and then everything out here, this is kind of known as the tail. Okay, so this is the tail, and this would be also be a tail. So what's not in the middle and kind of going off to the edges, these are known as the tails. And so I would say, you know, these two tails are, you know, this one's a little bit longer than this one, but it's not like this one is drastically longer than the tail over here. Okay, right? This tail goes from, I mean, it is longer, going from about 120 or 140, depending on how you decide to draw it. It goes from over here to over here, spanning anywhere from 80 to 100 points. In terms of cholesterol levels, and this one seems to span 40. Okay, so this tail is technically longer. Okay, so the tail to the right is a little bit longer. Is a little longer than the tail to the left. Okay? And so you might say this is slightly right skewed. Okay, so a description of the shape we would say there's one peak, which we then say unimodal, like a unicycle. Unimodal. So two peaks would be bimodal. And we have a slightly longer tail on the right, so we might say slightly right skewed. So here is, I don't know, are you guys still writing, or is this okay? Okay. So here's another distribution. Here we're looking at distributions of heights in a class, and they chose to draw the bins a little bit differently. And this one looks like the tail on the right and the tail on the left are around the same, and so we would say it would be symmetric. It's unimodal and symmetric, maybe ever so slightly right skewed. Okay. You know, here, if we looked at this one seems to change, and now it looks like we've got two peaks. Okay, we got a peak over here and a peak there. And so we might say this one, if we look at the data this way, we might realize that, oh, the data is actually bimodal. And here we see the tail actually a little bit more pronounced to the right. And so we might say is a little bit more right skewed. Okay, so we'll say this is actually the same underlying data, and it's just we've changed the way we've displayed our histogram. Okay, but having a little bit more detail, we say, oh, actually the data looks to be slightly bimodal or a bit bimodal, and maybe the right skew is more pronounced. Okay, and here's this is an example of having your bin widths too narrow. Okay, and so when you ask people how tall are you, they normally just say like I'm 5'4" or I'm 5'10" or something like that. But some people might say I'm 5'4½". Okay, and if we created really thin bin widths, then we might see a few people in these kind of in between 5'4½" numbers showing up in their own bin, and so you get this funny looking thing. Okay, which is probably not ideal, because this is more an artifact of people's self-reporting than actual measurements, right? If we actually took your measurement, we could get really accurate numbers, and we would see you're not 5'4½", you're actually 5'4.1673" or something. Okay, but because when we ask people to self-report, they give off all these different things. Okay, so anyway, we could summarize a histogram with just kind of this nice smooth curve, and this page in your textbook will say, okay, so here we've got unimodal distribution that's symmetric. Here's another unimodal distribution that's symmetric but not bell-shaped. This is unimodal, but this is skewed left because you've got a tail going to the left, and you've got a skewed right because you get the tail going to the right. Okay. If you're going to have trouble remembering this, just think of if you had to skewer some meat, which side would you use to do the stabbing? You would use the right side on this one, and you would use the left side on this one. Okay, so you got skewed right and skewed left. Okay, so let's just think. I'm going to throw out a distribution here, or throw out a numeric variable, and you tell me symmetric, skewed right, skewed left. Income levels in the United States. So don't shout out your answer. Think about it, okay? Income level, or just income, annual income in the United States. It's a numeric variable. Do you think this is going to be symmetric, skewed right, or skewed left? Okay, don't shout it out, but just think. Income. Income in the United States, or actually income in the world, really. Okay, what do we think? Income is skewed right. Okay, so to be skewed right, it means our thing looks like this. Okay, and so remember, this is a numeric variable going across here. And so if you think of most people in America probably make between, I don't know, 30,000 and 100,000 a year. Okay, so whatever, you know, this will probably be the bulk of people, right? 30,000 to 100,000. Okay, most Americans will be somewhere in this range. Are there people making $1 million a year? Yes. Okay, so $1 million a year. So if this is 0 down here, 1 million would be, I would have to take this from 0 to 100 and look at 10 times that. So this would be 200,000 and then here would be 300, and here would be 400. Actually, it doesn't even fit on my page. Okay, but there would be somebody out here at $1 million a year. Okay. Can you have an annual wage less than $0? No. Okay. I mean, maybe somebody, you can't have an annual wage. You might owe people money, but that's not your wage from working. You can't be lower than 0 here, okay? And so what we see is we're going to see something right skewed. You're going to have people making $400,000 a year. Not a lot, but you will have people out here, okay? Whereas most everyone else is going to be over here, okay? Most everyone's going to be in this this zone. You're going to have the bulk of people in here. And then, yeah, this is the 1% would be out here, okay? So that's, so income is right skewed. Does that make sense? Can you guys think of anything that would be left skewed? I'm going to run out of time as I keep talking here. This is bimodal, and these are other shapes here. Okay. Left skewed, left skewed. Obesity? So what do you mean by obesity?
People's weight.
Okay, so people's weight, I would say, is actually right skewed. Okay, most people are healthy, normal weight. I don't know, maybe not healthy weight anymore, but most people probably between 100 and maybe let's say 220 pounds or something like that. Okay, the bulk of people. Are there people who weigh 400 pounds? Yes, not very many, but there are, okay? Let's say the average weight in America is 160 pounds, something like that, okay? So 400 pounds would be 240 pounds over average, okay? So that's way out, well, in this case, way out over here on the right, okay? Can anybody be 240 pounds below average? If the average is 160, can you be 240 pounds below average? No, because that would take you to negative 80 pounds. Nobody can weigh that. Okay, and so you're going to have kind of a cutoff over here. You're not going to really see people weighing less than like 80 pounds or something. Okay, most people kind of in this normal range, but then yes, we have some people who are very obese and weigh very much. So that would still be right skewed. Okay, things that are left skewed would be like test scores on an easy test. Okay, or relatively easy test. Maybe most people will score between 80 and 100%, okay? Can you score over 100%? Well, I guess depending on the test, but generally no, okay? So you can't score over 100%, but most people will be between like 80 and 100. Could there be a student who gets 20%, 10%? Yes, okay? And so you're gonna have this distribution where most are up here, and then you have a few people down very much lower. And that would be left skewed. Okay? And again, so whenever we're talking about the shape of a distribution, you have to think of the underlying numbers being represented. Okay, so we have, so we talked about shapes of distributions. I want to talk very quickly about box plots. Box plots which require, oh dear, Q1, Q3, and the IQR. Okay. So the median, we've already established, the median is the halfway point. So we can think of this as the 50th percentile. Anytime you have the percentile, that means when I say 50th percentile, the translation is that 50% of the data is smaller than the 50th percentile. So whatever number I stick in for percentile, that is the percentage of data that's smaller than that. So if I say the 25th percentile, what percentage of data is smaller than the 25th percentile? 25%, okay? Okay, and the 25th percentile is Q1. Q1 is the first quartile. So it's the first quarter of the data is smaller than the first quartile. The first 25% is smaller than the 25th percentile, or the first quartile. 1/4 of the data is smaller than the first quartile. Okay, so what percentage is smaller? What is Q3 equivalent to then? 75th percentile, the third quartile. 3/4 of the data are smaller than the third quartile, or it's the 75th percentile, meaning 75% of the data is smaller than the 75th percentile. Okay. The IQR is the interquartile range, and it tells us the distance between Q1 and Q3. Okay, so if there's a great distance between Q1 and Q3, then that means the 75th percentile is very different from the 25th percentile. If the IQR is small, then that means the 75th percentile and 25th percentile are not very different.
You're saying that when you go from 25% is smaller, and 75% is even smaller?
No, 75% is smaller. 75. Okay, sorry. I should write the full thing down. 75% of the data is smaller than Q3. And over here. So these are locations, right? So we're just kind of marking off locations in our data. We're saying this is the 50th percentile. 50% of my data is smaller than it. This is Q1. 25% of the data is smaller than this value. Over here is Q3. 75% of my data is smaller than this thing, okay? And the IQR is the distance from Q1 to Q3, or we can just say IQR equals Q3 minus Q1, okay? And so if the IQR is big, it means 75th percentile and 25th percentile are very different. If the IQR is small, then that means your 75th percentile and 25th percentile are very similar to one another, okay? So let me think of a example. Let's say we took house cats, okay, and we managed to weigh 1,000 house cats, and we looked at the 25th percentile of house cats and 75th percentile of house cats. They're probably going to be within a few pounds of each other, okay? You know, you're going to have some really extremely heavy house cats, but they're not going to be in the 75th percentile. They're going to be in the 90th or whatever, okay? So the bulk of house cats are going to be, you know, 75 to the 25th percentile. You're probably just going to have a few pounds of difference. On the other hand, if we looked at dogs, okay, and we looked at the 75th percentile of dogs and 25th percentile of dogs, we see there's a great range, right? Because dogs, you can have little dogs, like little terriers and things like that, and you can have big dogs. And even if we looked at the 75th to the 25th percentile, we're probably going to see a great difference between a dog on the bigger side and a dog on the smaller side, right? You think of a cat that's slightly on the big side and a cat that's slightly on the small side, they're not going to be that greatly different. Dogs, a bigger dog versus a smaller dog, you're going to see a bigger difference there. Okay? the range, so the IQR is the interquartile range, and the range, the plain old range, is the distance from the max to the min, or distance from the min to the max. Okay, so the range, max minus min, the biggest data point minus the smallest data point. Okay, range is obviously going to be affected by extreme points, data points or outliers that will define the range. We are right about to run out of time. Well, I do believe that Chapter 2 is relatively straightforward enough for you to accomplish and understand on your own. Where if you work through the problems that I've assigned as the homework and you view the solutions, I think you can get a good handle on them. Okay. The last thing I want to talk about just very quickly is the standard deviation. I have a video that I've prepared online talking about the standard deviation. But the key thing here is this is just another way to measure spread. Measure of spread or dispersion. And we have 3 ways to measure spread. Okay. Spread can be measured with the range, the IQR, and the standard deviation. And all these do is they just put numbers into how far apart your numbers are spread out or how close they are together. So you can think of the weights of cats, house cats. Most house cats you encounter, they look about the same size, right? I mean, you've got some fat cats and some that aren't so big, but most house cats you encounter, if somebody says, I've got a cat at home, you're expecting a creature about this big, okay? If somebody says, I have a dog at home, and they don't say anything about that, you don't know if the dog's going to be this big or if the dog's going to be this big, okay? So when we look at the numbers regarding spread, all of these numbers, range, IQR, and SD, will be very small for cats because you don't have that much spread. Somebody says you have a cat, you're expecting a creature about this size. You're not expecting a whole lot of variation. But when we talk about dogs, you're going to have large range, large IQR, large standard deviation. They're all different ways of measuring this idea of spread. And we probably won't get to go into the nuance between the different measures of spread, range, IQR, and SD, like we did with the mean versus the median. But these are, again, the thing to keep in mind is there are ways to measure spread. So I'll say cats, small spread. Dogs, large spread. Okay, you can have little dogs, and you can have big dogs. I have a daughter, and her favorite book right now is Go Dog Go. I don't know. They talk about big dogs and little dogs. Black and white dogs. Okay, but cats, you know, the little cat is going to be like this big. This looks exactly like my, and then a big cat is going to be like the same size, right? Okay, these are terrible pictures. So anyway, we have that, and the range, IQR, and standard deviation, these are just different ways to quantify this component of spread. Also keep in mind these are still summary statistics, and we are just summarizing a whole bunch of numbers with a single number, okay? We're just saying, here's, 200 data points, and we're summarizing it with one number. we might be summarizing the measure of spread with a single number like the range or the IQR or the standard deviation. These are summary statistics to just kind of give us an idea of that. Do your reading for chapter 2. I feel like this chapter is straightforward enough. Do your homework. Any questions you have, you can check out the videos. You can also email me, and I'll be here a little early next week for office hours. Well, every week. So, okay. Well, looking forward to a great quarter. We'll see you guys next week.